Qx divided by T. Okay. That's where you see, oops, my computer crap out again and come back in. Okay, I do apologize. Okay, so that's where, oh, things went missing. Always they do this. Okay, when they jump in and out. So that is where you have Vy over I xx Qx divided by T. Okay. Okay, so what I was saying is this is where the topic gets very extensive, because we have applied what we have learned for the past 6 weeks into one problem. Okay, and again the next 2 weeks later on we have to apply Mohs circle again. Okay, right. So now we know the formula that we're going to use. Okay, so we know that there's no torque. Okay, for this question, there's no torque. Later on, we will deal with it. I will teach you how to analyze whether is there a torque or no. Okay, so that's a blessing. We have no torque for this case. Okay, okay, just to let you have. But we have Vx and Vy. Now the shearing stress over here, we're going to apply thin wall analysis. Okay, so this is me forewarning you what we have. Okay, we have thin wall analysis, and then the moment over here, as you can see, the moment over here, what we have is an eccentric, unsymmetrical, loading. Okay, so we have a lot of components over here. Okay, but it's not that difficult. Okay, once you apply the rules that I gave you, okay, it's pretty straightforward. Okay, so the first thing is the first step procedure. Step number 1, we're going to determine the axial force, bending moment, shear force, okay, and torque if there's any. Okay, so let's get the image. I will use an image. I'm going to increase the intensity of my screen because it's, yep. Okay, so let's get this image. Okay, and again, do what I mentioned. Draw everything in 2D. Okay, so we already have sketched out our transformation. So we know that this is our X, this is our Y, and this will be our Z. Okay, so let's sketch up our transformation, and then let's analyze our structure. So the first thing we are going to look at the exact plane. So you sketch out. So this is our X, and this is our Z, and using right hand rule, that is our rotation, and a Y. Okay, so I'm going to sketch that now. So I'm going to draw wait, so this is the height, and then I'm gonna, okay, and then we have hidden details, the beam. Yeah, have to be more defined. so you guys know where we're looking at or what we are looking at. Then we have our element A, and then we have our element B. Okay, so now you know where we're looking at. Then again, sketch out the position of the neutral axis. Okay, and then this over here is built in. Then over here, this is our neutral axis. Then we put in our forces. We know that we have one force coming down here. It's at 100 kilonewton. And then we have a force pushing into the structure, which is 25 kilonewton. And then we have another force coming in this direction. So this is 8 kilonewton. Comma means you're aware that there's twice. Okay. So now we are going to analyze the structure. So the only forces that we're going to look at is at this 100. Okay. And the 8 kilonewton twice what it's going to do. Okay. So now we start. Right. So the first thing we're going to do, we know that PZ is equal to minus 100 times 10 to the power 3 Newton. Okay. So we know that PZ is going to induce a stress in the Z direction over, so stress Z is equal to PZ divided by A. And now is where the analysis, and you know that element A and element B, both of them are going to be in the negative. It's in compression. Okay, so write this out. Okay, this is where the analysis start. Okay, don't break down all the forces already, then later on you get confused. Is it going to be tensile compression? You write all this down. Okay. Then you look at the 8 kilonewton the twice. Okay. So we know that there will be a moment in the y direction. Okay. So we know there is a, or we just put in there is, or there. Okay, I just put my. Right. There's a moment there, and the force is what? Perpendicular to the neutral axis. Yes or no? Right. So therefore, distance is applied force to the element. Right. Okay. So we know by looking at the diagram over there. So moment in y. Okay. So moment in y. So I'm going to take positive is going in the anti-clockwise direction. So moment in y will be equal to twice 8 times 10 to the power 3. Perpendicular distance, as you can see, it is what? 0.6 meters. Yeah. So this is equal to 2 times 8 power 3 times 0.6 is equal to 9,600 Newton meter, and it's going in this direction. right? So you draw your moment vectors. You start drawing your moment vector in y is in this direction, right? And the head of the element of the moment vector is compression, right? Sorry, I'll put down here compression. The tail end is going to be what? Tensor. So from here, we write that stress Z is equal to my over Iyy multiplied by x, right? So for element A, right, it's going to be compression, right, relative to the neutral axis. And for element B, it's going to be tensile because it's on the right hand side or the tensile side of the moment. So this is what I've taught you guys before in week 1 to 3, yes, or 2.5. Okay, when is it compression, when is it tensile? Just by looking at the moment vector. Don't just rely on the formula, just look at the moment vector. Then another one that we have, so we also know that we have, if I'm going to call this positive, so Vx, we're going to have a shear force in the x direction, which is going to be equal to twice 8 times 10 to the power 3. So this is equal to 16 times 10 to the power 3 Newton. Now, we are going to look at what is Vx going to do. Okay, right? So we know that the formula we are going to apply is the shear stress is equal to Vx over Iyy Qy over T. Okay, so let's look at the cross-sectional view. Okay, we have to look at the cross-sectional view for this case. So I'm going to come here, look at this diagram, get this diagram, and I'm going to paste over here. Okay. So we're going to, as I mentioned again, okay, I'm going to let the diagram be big down here. Right. So we are going to look at thin wall analysis. Okay. Okay. So this is where our element A is. Over here is where our element B is, right? So we know that the shear force is coming in this way. So this is 8 times 10 to the power 3 Newton. This is 8 times 10 to the power 3. That's where it's 16. Then we sketch the what? We sketch the shear flow, right? Sketch the Q. So we know that the web controls the flow. Right, and then this thing will be coming in. So what we discover is this. Okay, what we discover. So these are all our terminals. And over here, the arrow is coming both ways. Is another terminal at the center. Yes or no? Okay. So what we realize over here in terms of shear, right? Element A will not be equal to 0, right? Element B, the shear will be equal to 0 because it's a terminal. Both arrows are coming towards it. It's a terminal, and both arrows have nowhere to flow. Okay, so this is where, yeah, I understand it requires a lot of memory, okay, a lot of analysis. Okay, so what I propose, we go for a break now. Okay, we come back in 5 minutes.
Professor, I have a question.
Yes.
For the neutral axis, like I know for the